Oh my god. Oh, good lord. Y'all, this thing freaking works. Hi, I'm Ara, N6ARA, and today I'm going to be taking you through the journey of how I built this, the TinyGawant. A while back, I noticed several folks on social media sharing photos of this weird whip antenna with an adjustable dial on it, but I wasn't able to find much info. I eventually saw a post that called it a Gawant antenna, and that led me to Alain, K1FM's webpage that talks about it. On his blog, Alain covers the history and design and even provides build instructions in a YouTube video demonstrating it operating in the field. It turns out the Gawant antenna was originally designed by Ariga-san JF1 QHC in Japan. The name derives from a combination of the city name Shinagawa and antenna, thus making it Gawant. Now, if you're like me, the first thoughts crossing your mind are, how does this work and where can I buy one? In some of the posts I found, I saw piles of these things and figured someone must be selling them online, but all my searching came up short. I really tried everything. Yeah, that didn't work. Now at this point, I thought about following Alan's build instructions, but figured I should understand the design first, then complicate my life more by designing a custom PCB. Okay, so this design looks fairly simple, right? You have an RF input that feeds into a transformer with a 2 to 12 turns ratio, so 2 turns on the primary side, 12 turns on the secondary side, and that results in a 36:1 impedance transformation. In parallel to that, there's a variable capacitor that you're supposed to dial and tune until the antenna network presents a 50 ohm load or a 1:1 SWR at the RF input. Now keep in mind, this design in particular with its turns ratios is for the 20 meter to 10 meter band, or 14 megahertz to 28 megahertz. If you want to say run it from 7 to 14 megahertz, you're actually going to have to change the turns ratio to make that all work. So this design kind of confuses me just a little bit, because if we were to remove this whip antenna entirely, you could select the right values for L and C and tune this until the input side sees a 50 ohm load or a 1:1 SWR. But in fact, you wouldn't really have an antenna, right? You don't have any sort of radiating elements, and maybe you could pick it up in the near field, but you're not having any sort of far field propagation. And essentially, you would just have current circulating here and dissipating as heat. Now, by adding this whip antenna, you introduce this radiative resistance, where when current flows across it, it'll radiate out to receiving stations. But you also introduce parasitic capacitance and, in fact, some series inductance. And so that's going to, if you were to bring the whip antenna in after dialing this all to resonance, it would actually detune the network. And so what you'd need to do is dial that capacitance until everything comes back to presenting itself as 50 ohms to the input side. Now, and this is my guess, I'm going to guess most of the current is actually going to be circulating here in this LC circuit, but just a little bit of current is going to travel up this whip antenna and radiate out. Now, I have a hunch that this is a fairly high Q circuit, and we may have a lot of trouble trying to bring this into resonance. So, small movements on this variable capacitor may actually shift the frequency around quite a bit, and so we may have to sit there and dial back and forth until we nail it on the exact frequency we want to be operating at. And in fact, the band might be quite large, and so anytime we want to do any sort of frequency hopping or moving around in the band, we're going to have to probably go back to this capacitor and dial it around to get a reasonable enough SWR so that we could put power into the network. So I don't anticipate this being a very top performer, right? It has a very short whip, nowhere near the lengths required to operate efficiently from the 10 to 20 meter band. But for SOTA, and with the band conditions being high, this might just work. And frankly, I think the next step is to put this into the schematic capture software, build it, and try it out. Let's go. Okay, so for the schematic and layout, I use KiCad. To start, I first made my own polyvaricon capacitor symbol and footprint, as I wasn't able to find one readily available anywhere else. I then placed the transformer symbol, BNC connector, and two 90-degree M3 screw terminals for mounting the whip antenna and counterpoise. Next, it was onto the layout. My goal here was to make the board as small as possible while minimizing parasitics. I placed the antenna and counterpoise where I thought it made most sense, then let the capacitor, transformer, and BNC fall into place based on the schematic design. From there, I routed all the necessary traces and tried to avoid overlapping signals between the top and bottom layers to reduce parasitics. And once the layout was done, I checked the 3D model, made a few tweaks, and then imported it into Fusion 360 where I catted an enclosure to protect it and a knob with an indicator to help tune the capacitor. Once I was satisfied with the design, I ordered the boards and parts. After the boards arrived, I inspected each side for defects and even fit checked some of the components prior to soldering them on. So we have our PCB, our variable capacitor, this BNC connector that'll fit on edgewise to the board. We have these screw terminals that are M3 and will snap into the board and solder on. We have this iron powder ferrite. It's a -6 mix and I believe a T50 size. I also have this nice little thumb screw for the ground radial at least. And then finally, the whip antenna itself, which will fit on top. And so to start, we're gonna have to wind a toroid. I know that's not everybody's favorite thing to do, but I usually like to do that first to get it out of the way. So I got my enamel wire here. Let's get started with that. The primary winding first, so that's gonna be the red 24 gauge. I think this should be more than plenty for 2 turns. Primary side done. Next up, the secondary side, we're gonna do 12 turns of this. All right, so we're going to start on this side. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, let's see if we can get this on there. All right, looks good enough to me. Let's solder it on. Not my best work, but it'll do. Okay, so the next step now is to integrate the variable capacitor onto the board. But before we do that, we need to note where the legs are on this capacitor. Just based on the way it's constructed, there is a clocking that needs to be matched to the board design based on where the grounds are and how the capacitors inside here are all interconnected. So at least for this layout, the side with the 2 legs needs to go on the toroid side, and then there's another center conductor here with 2 legs that will go on the antenna side. It's honestly a little trickier than it really needs to be to get this thing on. All right, so this is interesting. It looks like the capacitor does not sit flush against the surface of the board, and so it can kind of tip around. I think what I might do, because if I were to install the screws here and crank down, this might end up sort of lopsided, and yeah, soldering it on will stiffen it up a bit, but I think what might be nicer is to design and print a little spacer that goes in here so the load path isn't through the legs of the capacitor, and then we can keep going. Next, I took the dimensions of the capacitor and used Fusion 360 to design the spacer. I also used this opportunity to finish the CAD model of the enclosure and adjustment knob. Then once I was happy with everything, I sent it off to the 3D printer to turn these models into reality. Okay. So we got the 3D printed spacer that seems to fit pretty well with the variable capacitor, and that leaves a little bit of room so that when I solder these legs, I don't end up melting the spacer inside. So let's give this a try. Feels pretty stiff. when you have the spacer in there now. I bet when we solder these legs, it should hold in pretty well. Okay. Okay, so next up is the BNC connector. A while back I came up with this trick where you can actually use these through-hole, almost I think like, straight board mount BNC connectors that are typically supposed to go flush against a board. Instead, you can actually put the center conductor pad on one side of the board, and if you make your board the same thickness as the distance between the center conductor and the ground pins, and provide some ground pins on the other side, you can actually kind of slot it in like this. And so the center conductor makes contact with one side and the ground on the other. And it actually works pretty well. So you solder it in, and yeah, it's not the most mechanically sound way to do it, but so far I haven't had any problems, and I think we'll have to come up with some, I think the structure is probably gonna have to take a little bit of the side loading so we don't end up damaging and breaking the pin on here. Solder up the center pin first. Okay, that's pretty good. Okay, so let's do the other side. Now for this one, I think I might just use a little bit of flux. Yeah, this part always takes a little longer because the BNC connector has just so much thermal mass. It takes a while to heat it all up. I could use a larger soldering iron tip and get more heat there, but I think this is good enough. All right, next we'll put on these M3 screw terminals. They should just kind of snap right in. Sweet. Okay, so I'm gonna have to solder these down, but at least we have a full assembly here. Okay, so that's all the soldering we need to do. It's all put together now. The last few steps are to put on the knob and then test the casing and install the antenna and give this thing a try. So here's the knob. It has a little U-channel shape that matches the mechanical pattern on the variable capacitor. So in theory, this should just slot right over it. It's a little tight, so I might need to kind of improve that, but hey, all right, that works. Ooh, actually, take that back. Okay, well, it looks like the tabs for the variable capacitor are very close to the edge of the knobs. And also just realize, if you're gonna be turning this dial here, and if your fingers are kind of hanging over the knob, you can easily contact this antenna output and maybe burn your finger. So I'm gonna take this off and just trim all these tabs and make it nice and flush. Okay, so before you judge me for what I'm about to do, these are my throwaway clippers. You can effectively see daylight through them at this point. I've used this exact one for several years now, and I would consider that end of life. Wow, look at all that weight savings. All right, let's fit check the clearance for the knob. Come on. There we go. Cool. Oh yeah, that's a whole lot better. You can still, if you tried, your finger can strike this, but at least it's better than what we had before. Next, we screw in the retaining screw for the knob. All right. Wow, that actually feels really smooth. All right, so let's try the case out next. So this little groove here should match the BNC connector. All right, okay, not too bad. That's kind of lame. Just kind of wiggles in there. So it's not a perfect fit, but I bet if we put this antenna on, oh yeah, that's a whole lot better. It's not wiggling anymore. All right, all that's left to do is to put the counterpoise. This is a thumb screw, so it should be really easy to service and use in the field. It's all together. Okay, we have our TinyGawant here all built up. We're gonna hook it up to the SWR meter to see if we can dial this thing into resonance between 10 to 20 meter. And if it works, great, we'll take it out into the field and test it. And if it doesn't, it'll be back to the drawing board. So let's give it a try. All right, connects in. We're now gonna extend the whip all the way out. Okay, so we're ready to start dialing around. I think, if I'm not mistaken, if we were to turn the dial, this only rotates from 0 to 180 degrees. It doesn't go all the way around. 20 meter band is somewhere here on the left, 15 meter is somewhere in the center, and 12 and 10 meter are here on the right. So let's start with 20 meter, and I'm just gonna ballpark it. I'm just gonna guess it's around here. We'll give it a try. Wow, that was actually really close. Oh my gosh, I almost nailed it. I swear that was just a random turn of the dial. We just need to dial it to the right a little bit, so higher frequency. Okay, all right, not bad. All right, 1.47 to 1, totally usable. Next, let's try 17 meter. I think that's gonna be somewhere around here. Yeah, not quite there. Dang it, now I overshot. Oh, it's really close. All right, 1.56 to 1. Man, this thing is really, really sensitive. Just the most tiny movements of this wheel will move this resonant point around quite a lot across the band. All right, let's try 15 meter next. So I'm gonna kind of guess somewhere around there. Okay, overshot. I think I'm already learning from this experience that it's gonna be a pain to tune this. All right, perfect. 1.56 to 1, you know, not a perfect 1-to-1, but honestly, this is more than good enough to use in the field. 15 meter, check. Next, we'll try 12 meter, 1.4 to 1. So far, the best we've seen. All right, that looks great. 1.23 to 1. This thing is tuning up across 10 to 20 meter, just as advertised. Okay, so far we've been testing this with just the whip and no counterpoise. So let us try testing it with a counterpoise connected. I'm gonna hook up a 13-foot counterpoise here. Sure, it's indoor and it's not the most ideal ground conditions in here, but I'm really curious to see what effects that has on the SWR. So let's give it a try. Okay, so I got my 13-foot counterpoise here. Let's hook it up to the antenna and see what that does. Okay, so I haven't touched the dial since we tuned up on 10 meters, so let's start with 10 meter and see how that goes. Whoa. So the SWR across the band just got like way worse. I mean, we were down in the, you know, well below 1.2 earlier, but maybe it just completely detuned the antenna system. Let's see where it ended up. Okay, well, that's not a an expected outcome. So without touching the dial here, it seems to have made the SWR across the band, the 10 meter band at least, much worse. At least from what I can tell, there is no usable frequency at the moment. So I'm gonna try messing around and see if we can dial this thing until we get at least one, like close to 1-to-1. Seems everything I'm trying here is just not, I cannot get this thing to tune up on 10 meter at all. Let's try some lower frequencies. Let's see if we can get 15 meter to tune up. Okay, so 1.7 to 1. Let's give 20 meters a chance. Ooh, yikes, that's not looking good. Okay, so we're only at 1.73 to 1 around the CW portion, so that's not much better. Is it usable? Yes, but it seems adding the counterpoise is actually detuning and kind of making this antenna appear to be worse. How that affects radiation, I have no idea yet. One thing to note here though is that just because you have a good SWR doesn't necessarily mean you have a good antenna, right? I think the only way we're really gonna find out how this antenna performs is to just take it out and give it a try. So let's do that. We'll find out together. To test the TinyGawant, I packed my gear and I headed up one of my favorite nearby SOTA summits, Josephine Peak in the Angeles National Forest. It's about a 4-mile hike to the top and about 2,000 feet of gain, and it's just absolutely stunning the whole way up. Now you may be wondering why I don't just take this to a nearby park to test it first, and quite honestly, I'm not sure myself. I just know that SOTA gear needs to be tested in SOTA conditions. And I'm also here for the adventure. Oh, no way. There's actual snow on the ground. Oh my gosh. Well, I think some of you folks from colder areas are probably like, why on earth is this guy excited about snow? Let me tell you, as an LA native, This is not something I see every day. Oh my gosh, wow. Look at that. It's snow. It's real. I'm usually not too surprised by what I find on top of summits, but every now and then you run across something a little interesting. There's a whole porta potty up here on the SOTA summit, and in fact, I just realized this porta potty is actually in the AZ. You got porta potties on the air. Morning.
I think it's 15 miles.
All right.
From the ranger station.
Made it to the top of Josephine Peak. All right. 5,561 feet. And it is a gorgeous day.
Dude, I'm down. Don't have to sell it.
Here on the summit now, I brought the TinyGawant Rev A with me, 20 meters to 10 meters, along with the whip antenna that I'll nicely install on the top. So antenna set. Also brought the QMX with me, a talent cell battery pack, and of course the tiny paddle with a adapter to connect it to the QMX. So let's put all this together and give it a try. All right, so we got the QMX. We're going to connect it directly to the BNC RF. DC input goes to a talent cell. And now what we're going to do is this little 3D printed paddle adapter. It's a prototype. I'm testing it out, so we'll see. Might have to iterate the design a bit, but at least it worked at home. Whoop. Of course, I drop it on the summit. It just simply slides in, locks in, and now you have something that prevents the paddle from rotating around. And so we'll plug it into the paddle port on the QMX. All that's needed next is a important point here, but it needs to be a right angle audio connector. Otherwise, it'll jet out and interfere with the paddle. So, and that also goes for the DC barrel plug. So plug that in. We got our DC power, our audio, and our paddle, and now we got this thing. It's almost like a KH1. So let's see how this works. And I just realized I don't have 10 meters on this. Cool. I guess we're gonna try 15. Brought my rig expert so I can dial it in and troubleshoot any problems. Obviously this is not something you'd normally want to bring to the top of a summit with you. But what I think I'll do first is dial this antenna into resonance on 15 meter, connect it to the QMX, and see what the QMX reports the SWR to be. And if they all look good, we'll get on the air. Now, I don't expect you to be able to see the screen. In fact, I'm having trouble seeing the screen. And one thing I'm already learning is that this dial is really, really sensitive. The other thing I'm noting now that I realize it, is it'd be really nice to put some markers on the silk screen up here, so you know that 20 meters over here, 15 meters over here, and 10 meters is over here. Oop, overshot just by a bit. Oh man, that is sensitive. Almost there. Oh yeah, 1.7 to 1. All right, it's ready to go. So it's kind of hard to tell, but I'm seeing a roughly 1-to-1, 2-to-1 SWR. I don't quite know what the meter reads, but let's give it a try. Let's call CQ.
Oh yeah, 5. I thought it was even higher than that. Right to his car, but no money. Hopefully it's a turning point. We'll see.
339. Texas. Oh my God. Oh, good Lord. $599. 569. I'll take it. There's DJ. It's Devin. Y'all, this thing freaking works.
gosh.
Overall, this field test went great. I bagged 10 QSOs on 15 meter, however, I only made one on 20. I wasn't sure if that was due to the band conditions or if it was because my usual chasers had already worked me on 15, but the RBN was picking me up with an SNR ranging from 9 dB all the way up to 34 dB on 20, so I figured the antenna at least works on that band. That said, I not only activated the SOTA summit, but I also activated the park. Looking at the QSO map, it's clear that this antenna totally works. So what are the lessons learned from all this field testing? How can we improve the design for the next revision? For one, I think adding an SWR meter, or at least an indicator to tell you when you're close to resonance, would make a huge difference. While you can listen to the noise floor and get fairly close to the frequency you want to operate at, it's still not very clear as you tune around where the SWR dips below 2 to 1 or whatever the safety limit is of your radio. That would especially be helpful for folks operating with radios that don't have an SWR meter built in, like the CFT1 or the QCX Mini. The other thing I would add to this design, and we touched on this a little earlier, is expanding the band coverage. In this video, we built the 10 to 20 meter model, but if you were to add a few more turns to the toroid, you can actually make it operate from 20 to 40 meters. Yeah, okay, so I built this one on the side and just didn't have time to edit it into the video. So what if you were able to take these two antennas and combine them into one, simply by adding a switch? Imagine you could build one TinyGawant to rule them all. This is actually the Rev B model, but we'll be testing that in the next video. And in fact, we'll be testing the Rev C model. Okay, I haven't built the Rev C yet. We haven't gotten there yet. Time is linear, and I just haven't gotten to that part yet in actual time. And I'll also explain the counterpoise stuff. There was a whole lot of drama there. That's going to be another fun thing to dig into. So this is a lot of work. Speaking of a lot of work, I should say, this is my very first YouTube video. I would be really interested to hear what you thought. Were there parts that were too slow, too much detail, too little detail? I would love to hear from you. Drop those comments down below. And I guess the thing the YouTubers say, like and subscribe, tell your friends, send this video out via Morse code, I don't know, do what you want. Next time on N6ARA Electronics, I find more snow.
Oh my god, more snow.
I make friends with the locals.
Hi, excuse me, do you know if they validate around here? Ooh, man, you look like you're in rough condition.
I test the latest design changes of the TinyGawant.
Oops. Oh, jeez.
And I drop my camera.
Oh, shit.
See you next time. Bye.